Hello everyone, I'm Dr. Navneet Kaur, Associate Professor in Department of Electronics and Communication Engineering, Sagar Institute of Research and Technology College, Bhopal. Today I am taking my fifth lecture of subject Digital Signal Processing. In my previous lectures, I have discussed about digital signals, discrete time signals, and discrete time systems. Now, in this lecture, I'll be discussing about solution of constant coefficient difference equation, which is used to find solution of any discrete time system. Now, first we will see what is linear constant coefficient equation. The general form of linear constant coefficient equation is given by this expression. Yn means it is the output at any particular instant n. Here we have yn minus k, where k is from 1 to n. If I'll put k is equal to 1, I'll get yn minus 1. Then k is equal to 2, I'll get yn minus 2, and so on. Say if I'll put k is equal to n, I'll get yn minus n. That means this represents past outputs. Now, in second term, we have xn minus k, where k is from 0 to n. If I'll put k is equal to 0, I'll get xn, which is present input. If I'll k is equal to 1, it is xn minus 1, k is equal to 2, xn minus 2, and so on till capital M, which represents past inputs. That means the output at any instant n depends upon past input, past and present inputs, and past outputs. Now here AK and BK are constant coefficients and capital N is the order of the difference equation. Now, say if I'll assume that say all inputs are 0. That means in this equation, the second part of the equation will be 0 because I have assumed that inputs are 0. Here, the system is driven by the initial conditions. That means whatever the past outputs, they will be fed back to the system and the system will generate output at any instant n. In that case, yn will consist of only first term. So, in that case, the solution will be known as zero input solution, or it is also called homogeneous solution. Now I'll consider the second condition in which I'll assume that all the initial conditions are 0. If all the initial conditions are 0, that means in this equation, the first term is 0. And the output is driven by only present and past inputs. So in that case, the output will consist of second term. So in that case, the output will be known as zero state response or forced response. So my total response is sum of zero input response or zero state response. Now, if I'm finding total response or zero state response of any constant coefficient difference equation, the solution will consist of two parts. First is homogeneous solution, which is represented by YHN, which is same as the zero input solution. And the second part is for particular solution, which is calculated for a given particular input. So total solution or total response will be given as YHN plus YPN. So note that if I am finding total response or zero state response, in that case, I'll have to find homogeneous solution and particular solution, and then the addition of these two solutions will give me the total response or total solution Yn. Now, I'll see in my next slides, how can I find out homogeneous solution and particular solution? Now, first we will see how can we find out homogeneous solution. Now, I had already discussed that the total solution of any constant coefficient difference equation is represented by this equation. Now, if I take this term on left-hand side, this minus sign will turn into plus sign and both these terms will be combined. So, k will be from 0 to n. Now, Here we have assumed that A0 is 1. Now, in this case, we will assume, since I'm finding homogeneous solution, I'll assume that all inputs are 0. All inputs are 0. That means the right-hand side of this equation will be 0. So I'll have summation k is equal to 0 to n, ak yn minus k is equal to 0. Now we will assume that the solution of this equation is in the form of an exponential. So we'll assume this homogeneous solution to be lambda raised to power n. Since YHN is equal to lambda raised to power n, if I'll put n minus k in place of n, I'll get lambda raised to power n minus k. So in this equation, I'll put lambda n minus k because this homogeneous solution is the solution of this equation. So it must satisfy this equation. Now I'll get k is equal to 0 to n, ak lambda n minus k is equal to 0. Now I'll expand this summation. If I'll put k is equal to 0, I'll get a0 lambda raised to power n. So this is my first term. If I'll put k is equal to 1, a1 lambda n minus 1, which is second term. Then if I'll put k is equal to 2, a2 lambda n minus 2, which is third term, till k is equal to capital N, which is an lambda n minus n is equal to 0. Now we know we have assumed a0 is equal to 1. So in place of a0, we will write 1. So we will get this equation. Now we will take lambda n minus n common from all these terms. So I'll get this equation after taking lambda n minus n common. Now this term inside the bracket is known as characteristic polynomial of the system. Now we can see this polynomial has n roots, which can be represented by lambda 1, lambda 2 till lambda n. These roots can be real or complex value. Now we will solve this characteristic equation and we will represent all the roots as lambda 1, lambda 2 and lambda n. Now we will discuss about the different cases when the roots of these equations can be real or complex value. Now, first we will see when the roots are first distinct. When the roots are distinct, then in that case, we can write the solution of homogeneous as C1 lambda 1 raised to power n, C2 lambda 2 raised to power n till Cn lambda n raised to power n, where C1, C2 till Cn will be constant, which can be found out later in the equation. Now, if we have case of multiple roots, the equation can be written as C1 lambda 1 raised to power n, C2 n lambda 1 raised to power n, C3 n square lambda 1 raised to power n, plus till Cn lambda raised to power n. Because we are having here multiple roots, so we have added n square to subsequent terms so that terms are not repeated. Now, we can understand this solution with the help of an example. So we will consider an example. Determine the homogeneous solution of the system described by this equation. Now, since we are finding homogeneous solution, we will assume input as 0. So right hand side will be 0. So yn minus 3yn minus 1 minus 4yn minus 2 is equal to 0. Now we will assume the homogeneous solution in the form of lambda raised to power n. So when we'll write yn minus 1, we will write lambda n minus 1. In case of yn minus 2, we will write lambda n minus 2. So I'll get the equation lambda raised to power n minus 3 lambda n minus 1 minus 4 lambda n minus 2 is equal to 0. I'll take lambda n minus 2 common. So equation I'll get which is given in the bracket lambda square minus 3 lambda minus 4 is equal to 0. So I'll solve this characteristic polynomial lambda square minus 3 lambda minus 4 is equal to 0. Now since it is a quadratic equation, it will have two roots, and by solving I'll get lambda 1 is equal to minus 1, lambda 2 is equal to 4. Since the roots are distinct, the homogeneous solution will be in the form of C1 lambda 1 raised to power n plus C2 lambda 2 raised to power n. Now, I'll put lambda 1 as minus 1 and lambda 2 as 4. Now we will obtain values of C1 and C2. Now we are given equation which is original yn minus 3yn minus 1 minus 4yn minus 2 is equal to xn. We will put n is equal to 0 in this equation by assuming input as 0, because here we have considered homogeneous solution. Now, from this is my equation 5th. Here in this equation, we will take n is equal to 0. So y0 is equal to c1 plus c2, and we will take original equation. In that equation also we will put n is equal to 0. So y0 minus 3y minus 1 minus 4y minus 2 is equal to 0. When we will take initial conditions, we will put the values of the initial conditions if they are given in the question. Say if initial conditions are not given in the question, then we will represent them by y of minus 1, y of minus 2, and so on. Now here, y0 will be equal to 3y minus 1 plus 4y minus 2. Now again, in these two equations, I'll put n is equal to 1 in both the equations. So in this equation, y1 minus c1 plus 4c2. And if I'll put n is equal to 1 in my original equation, I'll get y1 is equal to 3y0 plus 4y minus 1. So I'll get equation 9 and 10. Now we will put equation 9 in equation 10. So I'll get y1 is equal to this right hand side. On solving this equation, I'll get c1 plus c2 is equal to 3y minus 1 plus 4y minus 2. And after adding these two equations, I'll get another equation which is represented by equation 13. Now we will solve equation 12 and 13 to obtain values of c1 and c2. Now when I'll find out c1 and c2, this will be the obtained value of c2 and c1. If the initial conditions are given, then I'll put in a value of y of minus 1 and y of minus 2 here, and I'll find out c1 and c2. And if in this case the initial conditions are not given, then I'll keep c1 and c2 as it is. So in the homogeneous equation, where c1 is required, I'll put the value of c1, and in c2 is required, I'll put the value of c2, and this will be my complete homogeneous solution. So this is how we find out homogeneous solution. Now next we will see how we can find out particular solution. The particular solution is represented by YPN. It is calculated by assuming that output is in the same form as that of the input. For example, if input is UN, then the output is also written as KUN, where K is arbitrary constant. Now this is the table where I have given if input is in this form, then particular solution should be written as this form. If input is constant, particular solution will also be a constant. If input is UN, it is KUN. If input is ACN, it will be KCN. If input is in the form of a exponential, then it will be written like this. If input is in the form of a sinusoid or cosine, then it will be written as like this. Now it depends what is the input given in the question, then we will assume particular solution accordingly. Now we will understand this concept by solving an example. Now in this example, we have to find out the particular solution. The differential equation is given and input is given UN. Here input is UN, so particular solution will be assumed as KUN, where K is some constant. Now the given equation is yn plus 3yn minus 1 is equal to xn. So we will write as yn minus 1 here as kun minus 1. So we will put the value yn as kun, 3yn minus 1 as 3kun minus 1 is equal to xn. Xn is un. So I'll put all these values in this equation. So I'll get this. Now I want to find out the value of k. Now for finding the value of k, we will put the value of n so that none of the terms in this equation should vanish. So if I put n is equal to 0, I'll get u of minus 1. U of minus 1 is 0, so this second term will vanish. So I'll not put n is equal to 0. I'll put n is equal to 1, then ku1 plus 3k u0 is equal to u1. All these un values having value 1. So none of these terms is getting vanished. So I'll put n is equal to 1. Now if I'll put n is equal to 1, I'll get k plus 3k is equal to 1 and k is equal to 1 by 4. So particular solution will be k in place of k. I'll put 1 by 4. So k un will be written as 1 by 4 un. So this is how we find particular solution. Now, once we know how to calculate homogeneous solution and particular solution, these solutions can be used to calculate zero state response of the system, which is also known as forced response, in which we consider all the initial conditions to be zero. So what we'll do for finding the zero state response? First, we will find out homogeneous solution, which is also known as zero input response. Then we will find out particular solution. Then we will determine the coefficients in the homogeneous solution, and the forced response will be given as the sum of the homogeneous and particular solution. And we have to consider this in mind, that all the initial conditions will be taken as zero. Now, if we want to find out the total response, in that case also we will find out homogeneous and particular solution, and we will add these two equations, homogeneous and particular, and finding the coefficients of the homogeneous solution, we have to use the initial conditions which are given in the question. So this is how we find the total response of the discrete time system. Now this is all for today's lecture. Thank you.